Compiler construction number 17. So today we'll talk about the closure conversion pass. So closure conversion, its job is to take an R5 program and turn it into an R4 program. And the basic idea is that we're going to go through the program and identify all of the lambdas and turn those lambdas into a constructor for a vector, and then we're going to find all function applications and change those as well. So let's start from the simplest thing. Let's just talk about the type of closure convert. I'm going to call it as cloconv, and it is going to take an expression, that is the expression of the program, and it's going to turn it into an expression combined with a list of definitions. And when I say definition, what I mean is the actual definitions of our language. So like define, function, whatever. Okay. Now, the majority of the rules for closure conversion are going to look like this. So for instance, when you do a closure conversion for a number n, then you're just going to return that same number, n, and you're going to pair it up with an empty list, because there are none. Okay? There are no lambdas inside of here. But what about when we have an add? If we had an add of a left and a right, well, what we're going to do is we're going to turn this into an add of a left prime and an r prime, because the left and right inside of there, they may have more closures. And we're going to pair this up with all of the definitions on the left combined with all of the definitions on the right, where L prime and the left definitions is calling closure convert on the left, and then the right prime and the right definitions is calling closure conversion on the right. Okay, so these two rules are like 90% of the cases, because they don't really do anything. There are some rules that don't create any definitions, but what they do is they get changes. So for instance, suppose we have an application. So an application has the operator and the operands, right? Now what we're going to turn this into is actually kind of detailed. So there's a complicated part and a boring part. Here's the boring part. Yeah, boring part. It's going to turn into an app, all right, where we're going to have a vector ref. Actually, sorry. We need to modify this a little bit. Okay. So closure conversion, by the way, takes place on arbitrary things. So that means this rater may be a complicated expression. So what we need to do is we need to turn this into a let, where we'll say let f be the rater, okay? And this f right here, sorry, I want to be like super precise and talk about like what the data structures are. So it would be something like, this is the identifier f. So the identifier f. We're going to set that to be the rater. Now, what is the body? The body says we're going to apply the vector ref of the expression, which is the identifier f, and 0. That's going to pull off the pointer to the code. And then what we're going to do is we're going to apply this to the vector ref of the identifier f1. This is going to give us the closure. Then we're going to have the rands, and then we'll close the cons, close the app, close the f. Now it turns out that this rater has to be the rater prime, and the rands have to be the rands prime, because there may be lambdas inside of those. And we're going to combine this with the rater definitions, and with the rands definitions, where the new version of the operator and the rater definitions is what happens when you call closure convert on that operator. And the new RANDs and the RANDs definition is what you get when you call closure convert on the operands. And of course, we got to map this, right? Because we're going across all of them. Okay, so here's the rule for things like numbers, variables, and whatnot. Here's the thing for addition. Here's the thing for application. Now, one of the things that you may notice is that we use application nodes for calling every function, for calling lambdas, and for calling top-level functions. In our new language, R5, it also supports top-level functions. So how do we deal with that? Basically, what we need to do is we need to make it so that when you call closure convert and you give it a function reference, which remember we've tagged specially inside of Unicify, a function reference t, we actually need to turn this into the construction of a vector, because we need to make it so that those things will be allowed to be called like this. So we're going to turn it into a vector where we have t, the function ref t, as the first element. And then we also need to make it so that there is a closure there. And let's just make it so that the closure is just unit. And then, of course, there are no definitions inside of here. What this means is that now when we actually call this top-level function, we're going to pass it an extra argument. So because of that, closure convert, when it operates on a definition, and these are the definitions that come in to the top level, those definitions, you know, they have the name of the function. Actually, I guess they don't really have the name. I mean, there's a name associated with them, but yeah, let's just say that they're there. So there's the function, there's the return type, and then there's the domain, and then there's the body. Essentially what we need to do is make it so that when you call closure convert, what you do is you return a new definition that's the same name, the same return type, but its domain is bigger. It contains an additional thing, which is a pair of, nothing, some variable that we don't care about, and unit. This unit, by the way, is that unit, the one that we stuck into the closure. That's the closure. And then we have the old domain, and then we have the new body, body prime, and we combine this with the body definitions, where the new body, body prime, and the body definitions is equal to calling closure convert on the body. Because we have to go through every top-level function and see if it has any definitions inside of it. Okay, now the last rule that's complicated about closure conversion is the actual rule for what to do when you see a lambda. This is 17.2. Okay. So we see a lambda. So we'll do closure conversion, and we get a lambda. And a lambda has the recursive name, the domain. Actually, you know what? I put the range first with define, so I'll put it here just to be consistent. The range, the domain, and the body. Okay. Now, what do we need to do? There's a lot that's going to happen here. What we need to do is we need to return a vector. Okay, and this vector is going to reference a top-level function, and we'll call it nf for new function. And then what we need to do is we also need to have a vector where this vector contains x0 through xn. We'll close this vector right here. And then we need to combine this with the new definitions. We'll call this definitions prime. Okay, Now, what's going to go on here? There are a lot of things going on. So we'll say that NF is a fresh function, a fresh name, a totally new name. Okay, what else do we need to do? Well, one of the things that we need to do is we need to look at the body and transform it and find any of its definitions. So we'll call this body prime, and the body definitions. And this is what happens when we call closure convert on body. Okay. How do we get definitions prime, and how do we get x0 through xn? Well, definitions prime, it's going to be the new function definition combined with the body definitions, because we're going to add one more additional function. Now, what's the new function definition? The new function definition is a define with the new name, new function. The return type is the same as the range here. Now, what's its domain? Well, its domain is that it has the same domain as before, except that there's one more thing. So we'll call this the closure arg, and we'll combine that with the domain. And then we'll have body prime prime, and that's the new definition. Now, what's the closure argument? The closure argument is a pair where we have the name of the closure argument. We'll call it the closure name. And then we also need the closure type. All right? Closure name is a fresh name. I'll write fresh names right here. So we'll say closure name and new function name. So those are two fresh names. Now, what's the closure type? The closure type, it's going to be equal to a vector type where we have t0 through tn. By the way, I haven't told you what x0 through xn are. I haven't told you what body prime prime is. And I haven't told you what t0 through tn are. Those are the ones we haven't defined yet. Okay, now we'll do body prime prime next. So body prime prime, it is going to be equal to a let star, and a let star is just like the sequence of lets that we've seen before. Where what we're going to do is we're going to say that we're going to say that this is, so there's a list of things. So we have a pair of the recursive name R, right there, R. Let me lower it down a little bit. The recursive name R combined with a value, which is a vector of the new function name, well, a function reference to the new function name, NF, and to the closure name. Because remember, we have to be able to recursively call ourselves. That means that we have to recursively call this function with the closure that we started with. Then what we need to do is we need to have pairs of x0 being equal to a vector ref of the closure name and 0. And then we need to do that for each one of the variables up to n. And we'll close that let. And then inside there we'll have body prime. So at this point, we're basically done. The only thing left is that we need to say what x0 dot 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 is, what x0 through xn is, and what t0 through tn is. So what we'll say is that x0 of type t0 through xn type tn, they are free variables in body. What the heck does that mean? Well, a free variable is a variable that is referenced inside of body, but is not bound by any let that's inside of body, or bound by the domain. So we go compute what those are. Now, one thing that we could do, and by the way, we need to know what their types are so we can synthesize what this type argument is. Now, one way that we can do that, and this is what I would recommend. Well, okay, so one way you can do it is that like right here inside of closure convert, you could go off and search the body. That's going to be really annoying because you're going to have to do it constantly. What I would recommend doing is actually make it so that what your type checker does is your type checker, when it is processing a lambda, it will figure out what the free variables are and install them into that lambda. So actually this list, x0 through t0, will actually be a field of the lambda. It will say inside of there, here's what my free variables are. That's what I would recommend doing. It's very convenient to work that way. All right. And that's actually all you need to do. Oh yeah, I guess there's kind of one last thing, one little detail, which is that how do you like stitch it all together, right? So you're going to be closure convert is going to be called on a program that has some info, some sequence of definitions, and then some top level expression E. And what you're going to do is you're going to turn this into a program where we have info, and we're going to have the definitions prime prime and the expression prime, where the definitions prime and the new definitions is equal to mapping closure convert over the definitions, and then E prime and the new definitions, let's call this new definition 0 and new definitions 1, is what we get by calling closure convert on E. And then the definitions prime prime is just equal to the normal definitions, combine those with the new definition 0, combine those with the new definitions 1. Now we got them all, we collect them all. So we can closure convert the body, we closure convert each definition, we take all those sets of definitions and we stick them up in the body. And so what this does is it now makes it so that we have walked across the whole program and found all of the definitions that we need. The thing that's cool about this is that it shows that we can add a new complicated feature to our programming language, like closures, without actually modifying the rest of the compiler. All the features that we need were already in our language. We just had to modify the front end. And one of the things that you're going to find is that the language that we've made, pretty much all of it, pretty much any feature that you could want is already in here. Now, of course, there's no like multiplication or something like that. So, I mean, there are more things that you would add, but essentially, really all that means is that you're going to have to add a whole bunch more instructions that are provided by your architecture. Like you're going to look up like, how do I do, multiplication? How do I do division? How do I represent a floating point number? But that's all like, I call it sweat work. You know what I mean? It's like you don't need to use your brain to figure out new concepts for adding those things. You're just going to go add them all by rote. And then other features will be more interesting, like maybe you want to add like continuations or something like that. Well, you can add continuations entirely by adding a pass-like closure conversion. The way to add continuations is called CPS. Or what you could do is you could actually change the compilation algorithm by making it so that, like the C level supports continuations, or maybe you would make it so the X level supports them. So every time you add a new feature, there's basically this question that you ask. I have these different languages. I have R, C, and X. Which one is going to be the one that implements this feature? Basically, like, because remember, we have arrows that go from R back to R, and C back to C, and X back to X, and we have conversions from R to C and C to X. Now the question is, I can, when I add a feature to my language, which one of these arrows change? What we just did is we added something inside of here, that's what closure convert is. Closure convert is like right here. And what that did is it added the feature of closures. In contrast, when we added the feature of top-level functions, we actually had to modify R, C, and X. When we add the feature of there are variables in the program, we have to modify R, C, and X because we have a process down here to get rid of variables. So one of the things that you're going to find is that there are tons of features that can be added entirely inside of R, and that's cool. All right, that's the end of our discussion of closures, I'll see you in the next one.